Bueno, buenos días y bienvenidos al Día de la IA en la UPNA, ¿vale? Hoy es el día dedicado a la parte más científica dentro de la Semana de la IA. Tenemos la mañana dedicada a la investigación y la tarde a los trabajos fin de estudios, ¿vale? Good morning and welcome, Konrad. Thank you very much for coming here today to show us your work using AI for Earth observation. Hoy a la mañana el programa que tenemos es el siguiente, lo tenemos aquí, ¿vale? Vamos a comenzar con la charla científica Understanding Our Planet with AI de Konrad Heidler de la Universidad Tecnológica de Múnich, ¿vale? Después pasaremos a lo que es el seminario de investigación con los 14 doctorandos que van a presentar sus trabajos aquí hoy en 3 minutos cada uno, para luego pasar a la sesión de pósters que tendremos media hora para poder ver los diferentes pósters y pasarse cada uno por el que más le interese. Y después ha cambiado un poco el programa porque la idea era hacer aquí el coffee break a la vez que veíamos los pósters. Lo que vamos a hacer es ver los pósters y a las 12:30 tenemos un coffee break preparado ahí detrás, ¿vale? Y luego terminaremos el día o la mañana con la charla de Iris Domínguez. Muchas gracias, Iris, ahí estás, ¿vale? Por venir aquí hoy a darnos esta charla tan interesante sobre sesgos e inteligencia artificial, ¿vale? Antes de dar paso a Konrad, comentaros o recordaros que mañana todavía nos queda el día de mañana y el día siguiente en la Semana de la Inteligencia Artificial. Mañana tenemos un día muy interesante sobre arte e inteligencia artificial, con una charla sobre el impacto que va a tener la inteligencia artificial en el mundo de las industrias creativas y digitales. Y después tendremos, vamos a exponer los finalistas de los concursos de arte de imagen digital y de microrelatos, a los que los asistentes podrán hacer su votación, y tendremos también un premio del público, ¿vale? Bueno, os animo a participar en ese día y también en el del viernes, que tenemos los 3 talleres que ya les quedan muy pocas plazas, así que si os interesan, por favor, hacer la inscripción cuanto antes. Y también tenemos el mapatón solidario con Médicos Sin Fronteras, al que podéis acudir para realizar una labor humanitaria con 3 horas de vuestro tiempo, ¿vale? Muy bien, ahora sí damos el paso a Konrad. Konrad Heidler is a researcher at the Chair for Data Science in Earth Observation at the Technical University of Munich in Germany. He received his bachelor degree in mathematics and his master degree in mathematics in data science from TUM in 2017 and 2020 respectively. Konrad is currently pursuing his PhD studies. His main research interests are remote sensing, computer vision, and the mathematical foundations of machine learning. More specifically, he works on visual and probabilistic reasoning and self-supervised learning applied to the observation of cold and polar regions. Thank you very much for accepting our invitation to the AI Week. Now it's your turn, and then we will have time for some questions after the talk. Thank you.
Wonderful, thanks a lot for the introduction. And good morning, everybody, also from my side. It's a pleasure to be here. I'd like to start by just expressing my gratitude for the invitation, and it's a pleasure to be here in Pamplona, very nice city. So today I would like to tell you a bit about how we can understand our planet with artificial intelligence. So I'd like to tell you some tales from AI in Earth observation. Now, just briefly again, I guess we just did the introduction, so I can go over this very quickly. I'm from the Technical University in Munich in Germany. I'm part of the Future Lab Artificial Intelligence for Earth Observation, where I lead the group Visual Learning and Reasoning. And if you want to send me an email, this is how you can reach me. All right, what are we going to talk about today? First, I'm going to give you a small introduction on Earth observation. What is Earth observation? Why do we do it? What do we do? Then I'm going to go into artificial intelligence for Earth observation, why we need AI for Earth observation and how it helps us. I'm going to present some case studies on what we've been doing there. And finally, I want to introduce you a bit to, a bit to my work, my group's work in reasoning in Earth observation, which I think is a really cool topic that I want to give some space here as well. All right, so Earth observation. At any given time, there are hundreds or maybe even thousands of satellites orbiting around the Earth, taking pictures and sending them down to us. And this is just an animation from ESA, from their Sentinel-2 satellite, where you can see it's just kind of flying across the globe, taking pictures, and you can kind of think of it as like it's flying, filming a strip below it, and we can then use this data to analyze it and look at what's happening down on Earth. And of course, it's not just one satellite, it's hundreds actually, and this is just a very small selection of the satellite observation programs from NASA, the Japanese Aerospace Agency, and the European Space Agency. And the thing is, these satellites, they send us really a ton of data, lots and lots and lots of data. So if we look at the data volume, and this is just the data that we host at the German Aerospace Center in Germany, you can see here on the left the scale is in petabytes, which is 1,000 terabytes. This data is just exploding like crazy. We get large volumes per day. We get around 30 terabytes, which is, I guess, like the storage of around 30 laptops each day that we can look at if we decide to do so. And of course, we cannot do this all by hand, right? We need some kind of automatic way of analyzing this data, just because it's so much, and we want to use it. That's why we send these satellites to space. We want to use the data to understand what's happening on Earth, and we need to do this automatically. It's impossible to do it by hand. And we do this using computer vision methods. I'm sure you have discussed some of these already this week. These are kind of our like basic building blocks that we work with. We can classify objects in an image, we can localize them, we can even segment them sometimes here in the bottom left, where we just, for each pixel, say what class does this belong to, and we can also track individual objects using instant segmentation methods. And when we look at research in computer vision, we usually have images like this that were taken with a camera or with a smartphone. These are examples from the ImageNet dataset. And what tends to happen in these images is you have a very clear foreground and background. It's always these three colors that we also see with our own eyes, red, green, and blue. And there's really thousands of research papers already on this, on how to really well analyze natural images, is what we call them. And now if we go to satellite images, the story is a bit different. We don't have this clear foreground and background anymore. Some people, if we look at this here in the bottom right, for example, this is the city of Seattle. Some people care about the ocean, some people care about the buildings, some people care about the parks. So depending on how you look at these images, like this definition of foreground, background becomes very different. And also we have a multitude of sensors. We have these optical satellites. We have, for example, also radar satellites and so on, which I'll go into in a second, which give us images at varying resolutions and varying modalities. So we can't just use our basic computer vision algorithms, slap it on these data and be done with it. We need to actually think carefully about what we're doing and how we can optimally exploit the data. So now I'd like to show you some examples for these like varying resolutions and modalities. For example, if we look at this image, this is from the NASA MODIS satellite, which gives us imagery at 500-meter resolution. We can't see a whole lot of this in this image here, but it's very useful for things like monitoring agriculture, because we get images every day because it's such a coarse resolution. Then we can go into a bit better resolution with the NASA Landsat satellite, which has 30 meters per pixel. And that's very useful, for example, when we want to monitor land cover, to see, for example, we can see here there's a city, there's some green spaces, there's might be a river in the middle. You might have an idea where this is going. Zooming in even further, we have the Sentinel-2 satellite launched in 2015 by the European Space Agency, which just has a good resolution of 10 meters, where we can start to recognize individual buildings and get a clearer view of this picture. And finally, if that isn't enough resolution, we can also use aerial imagery, which really has like centimeter grade resolution, where we can see individual trees, we can see really fine-grained, we can see the markings on the street, everything. But of course, there's always a trade-off between we get low-resolution imagery very easily, very often. It's easier to analyze because it's less data, and the high-resolution imagery is more expensive to get. We get it less often, and it's just more data to deal with. So usually we try to make some trade-off between high-resolution imagery and low-resolution imagery to kind of be able to deal with this data. All right, let's talk about different modalities. So this is probably the most common kind of satellite imagery that we're used to, optical imagery. If you go to Google Earth, Google Maps, Bing, whatever, this is what you're going to see. And this is just really like a basic camera that is mounted in space and takes pictures of the Earth in these red, green, blue channels. And we can look at this, and it's the same kind of way that we're used to perceiving the Earth. We can see in green, we can see the vegetation. In yellow, we can see drier areas, snow is white, and so on. It's kind of the most natural representation for us humans. We can do the same thing at night, and that it looks a whole lot different. Nighttime images are very useful for analyzing where our cities, obviously, because we have all these street lights, all the advertisements, everything that lights up even into space, and we can see very, very well where the big cities are, where the roads are, using optical imagery acquired at night. Then we can do the same concept of optical imagery, but not do red, green, and blue, but for example, look at infrared images. This is a false color visualization from the NASA Landsat satellite, where we're looking at infrared, and this is very useful when we're looking at, for example, different vegetation, how healthy are the plants, how much water is in them, is there a drought? This is something that we cannot see as well in natural imagery, but we can see it much better in this infrared imagery. And finally, going away from optical, we can also look at Earth with different methodologies. This is synthetic aperture radar, which is very similar to radar systems that you have on like ships or planes, which kind of sends a radar signal from space to the Earth. It bounces back, and then we can, with an antenna, once again receive the signal, and it looks a whole lot different here. But the cool thing about this SAR data is it's not affected by clouds, for example, and we can get this all year round, basically. And it's very useful also because we can really measure very small changes in height and space using these radar waves. And finally, sometimes the imagery looks like this. It's not really imagery anymore, but there are also satellites that take very specific measurements that have no clear visual interpretation anymore. For example, here we have an image, or should we say measurement, from the NASA Cygnus mission, which it's really cool. What they do is they record the echoes from the GPS satellite. So you know you have the GPS that helps you localize your phones, and they send down signals from the satellite to the Earth. These signals are reflected from the Earth, and then this other satellite picks it up again. It's really fascinating. It doesn't look very helpful to us, but what we can do with it is we can analyze, for example, the moisture in the soil using this. We can analyze wind speeds or wave heights over the ocean because we get an estimate of the roughness of the water using this. And I'm going to show you one study using this kind of data a bit later today. All right. So I said we want to use AI for Earth observation because we cannot do this by hand. And the question is, of course, how can it help us? Why do we use it? I put 4 points here. First of all, we needed to analyze data, to just kind of break down these huge images into something that we can then work again with. We can use it to detect changes on the ground. Like many areas on the ground don't change at all, but sometimes you build a new building, trees are felled, this kind of stuff we can detect very well using AI on these satellite images. We can use AI to also combine data from these different, like for example, the radar imagery and the optical imagery. We can also combine that using AI to get better insights, which is called data fusion. And I put a question mark here. Maybe we can use it to predict the future. This is a very hotly debated topic, but of course it would be great for some applications if we can also use temporal machine learning to understand not only what is currently on the ground, but what may happen in the near future using machine learning. All right. Seeing this, my boss down here, Xiaoxiang Zhu, she founded the Future Lab for Artificial Intelligence for Earth Observation in Munich. So this Future Lab is kind of an experimental German way of structuring research, where we get money to establish this lab and work together with researchers all around the world, invite them to join us, and also closely collaborate with other people there. And the main topics of this Future Lab are reasoning, which you'll hear about later, uncertainties, ethics, and beyond. I'll talk about that in a minute. And we have a large team of people. If you look at this, we have people from around 40 international organizations from 20 countries, and work with around 70 people at all different professional levels. So we have PhD students, postdocs, professors, and visitors from all different grades of research. And we're also closely collaborating with other AI for EO researchers, both at TUM and the German Aerospace Center, DLR, which is also very close to Munich. All right, so our mission statement is we want to use AI and data science in Earth observation for tackling societal grand challenges such as urbanization, climate change, the United Nations goal for sustainable development through cutting-edge research, technology transfer, community building, and training. So I guess me being here today would qualify as community building, hopefully, and I'm going to talk about this cutting-edge research and technology transfer in a minute. All right, there we go. So these United Nations Sustainable Development Goals, I guess most people are not familiar with them, so I'd just like to show them to you here. It's a collection of 17 goals that the United Nations organization has kind of put forth that we should strive towards in order to live sustainably on the Earth and it will be in harmony with Earth. And we can see some of these points are very closely tied to Earth science and Earth observation. For example, here we have climate action, life in water on land, or we have, where is it? There's like life in cities or something, sustainable cities. All these things are things that we can monitor from space. So our research is very closely tied to these goals and kind of monitoring and tracking how well we are fulfilling these goals and maybe what we can do better to work on these goals. All right. As an overview of what we're doing at the chair, we always like to show these kind of images to give you a feeling for what our data looks like, what we're working on. In the top left, you can see we're working on urbanization, monitoring cities, how they grow, how they develop. We're working on natural hazards, so like floods, volcanic eruptions, earthquakes are also something that are very like large-scale events that you can see from space. We're working on food security, so monitoring agricultural development, monitoring droughts, monitoring heat waves, to be able to tell, okay, there's going to be a bad harvest this year maybe because we have a drought. And from space we can tell that even very early in the summer when other people may not know about it from the ground. Once again, these sustainable development goals, for example, mapping poverty, mapping informal settlements in developing regions, which are really large areas that the local authorities often don't know about and don't know how many people live there and so on, but you can of course see what's going on from space. Then we have crisis response. Here we have an image from the Beirut harbor explosion in 2020. And when we have an event like a disaster and have an image before the event and after the event, we can very clearly see which buildings were damaged, what happened, which areas are affected. And this is very important for the people on the ground who want to help the affected people to know where they need to go, right? And using Earth observation data, we can very specifically target regions that are affected. And the bottom left, you have climate change, which is my largest personal research topic. So monitoring anything in the cold regions, Antarctica, Greenland, how the glaciers are melting, monitoring permafrost, monitoring deforestation, all these kinds of things. And on the bottom right, some more experimental projects. We were working with Twitter data because there is a lot of geo-localized tweets available, which you can then combine with other geo-data to see, because what people are saying on Twitter really tells a lot about the local stuff that's going on, right? If you tweet, hey, I just had a great lunch here, it means probably you're at a restaurant. If you tweet, hey, this lecture is really interesting, you might be at university. And there's a lot of information to be gained from combining this text data with the Earth observation data. And finally, on the right, if you go into really like drone data or very highly resolved data close to the ground, you can also monitor, for example, here it's a car park where we can see that everything's okay, no accidents are happening, that kind of stuff. Right. Let's talk about, this was kind of the applications that we're working on. Let's talk about the methods or the AI approaches that we're trying to combine into this Earth observation. We have 8 points here, and this is kind of our main method development that we're working on. First of all, we want to combine physical knowledge about processes on Earth with machine learning. So a general machine learning model doesn't know anything about physics or anything. For example, when you want to map floods, there's very specific physical rules that the water is following, like the Navier-Stokes equations. And when we want to combine that with machine learning has no idea of these equations. So we're researching ways of combining both this physical knowledge that we have and that we should use with machine learning to get the best from both worlds. Then my research topic, reasoning. On the ground we have lots of objects which are in close relationship to each other. For example, here cars tend to be on roads, buildings are usually next to roads, and there's lots of relationships which we can exploit in machine learning to better understand what's going on. Then for transferability, Earth is big. So we often have the situation that we have very good data in some places, but we actually care about the situation in other places. And in machine learning, it tends to be that you have a model that might work really well on Central Europe or North America, and then you want to apply this model to, say, Africa, but it doesn't work at all. But there are techniques to kind of do this transfer learning where we can train a model on a data with good region and then apply this learned model by transferring it to a new data distribution, like, say, data from Africa. All right, going into uncertainty, this is also a very big topic in the earth sciences, because when we talk to the geoscientists, they always ask us, okay, but we have this prediction, but what's your error bar? How certain are you of your predictions? And the thing about machine learning models is they tend to be very confident in their predictions, even when they're wrong. So they will tell you, hey, this is a forest, and they give you 95% confidence, but in reality it could be a city or something. And in order to better understand the uncertainties in the models, there are specific methods to better understand where the model is certain and where it isn't certain, so that people can better trust our predictions when they're right and know when they may not be right. Very closely related is also explainability. So we often talk about the black box of AI. We throw a lot of data into our model, and then it predicts something, and it works really well, but we don't really know why. What's going on? Why is the model working so well? And to kind of uncover this black box, to open it up, we're researching methods to do, for example, attribution. Why does the model come to the conclusion it does? For example, here we have a prediction of a city, and we ask the model, why is it the city? And then we get this kind of heat map where we can see that it's focusing on the buildings in the city to tell us it's probably a city. All right, and the last three ones, AutoML, deep topology learning. I mentioned we take a lot of inspiration from computer vision because it's a very similar field. But most of the time the methods are probably not optimal because they were developed for a different type of imagery. And with AutoML or automatic machine learning, it's kind of learning to learn, learning what would be an optimal neural network architecture that we can then train, and doing this kind of meta learning to get optimal models for machine learning that we can then use. Quantum machine learning is a very experimental area, but very exciting because quantum computers can do things that cannot be done with normal computers or the GPUs that we have. They can, for example, compute with multiple different states. And this, once these computers get big enough, will be very exciting for data science applications, even though right now we're working with very small quantum computers, which are not super useful right now, but we're developing the algorithms, so one day when the machines get bigger, we can really exploit all of this technological advance there. And finally, ethics is super important because we're working basically like with data from the ground where people are living, right? There are privacy concerns when we have especially this high resolution data, where we look at people's backyards. That might not be a great idea to do this all the time, and we need to like really justify why are we doing that. And also, for example, when you think of the slum mapping that I was talking about earlier, just labeling one area as a slum, or we like to call it informal settlement, of course then has implications for the people living there, right? And these are also things that we need to keep in mind, that our research has an impact on people living on Earth again, that we don't just do science for the sake of science, but also do science for the greater good. All right, so as the first case study, I'd like to go into urbanization. If you look at these projections from the United Nations, you can see that already now the population in rural areas is kind of stagnating, whereas people in cities, the population in cities is going up like crazy. So more people are moving to the cities, moving out of the small towns, of the rural areas, and cities are growing. And if we look at a spatial map of where cities are growing, you can see here the world city population predictions around the world for the largest cities, and you can see the dark blue cities are cities that have already been large and haven't grown much, and the light blue cities are the cities that are really growing at the moment rapidly. So you can see we have lots of growth in South and East Asia, in Africa, some in Southern America, for example. And these tend to be also areas where we're not quite sure how these cities are growing, because the local authorities sometimes are overwhelmed with the rapid growth. And this is something where we can help from space. So I showed you some imagery earlier where we can really see just where the cities are from space. And then we can extract a product like this where we can see, okay, there's some areas where we have human settlements, and the white areas are areas where we don't have human settlements. And we can do that globally based on data that we have. And we have very good data in areas like Europe or the United States. But in other regions we have missing or incomplete data. For example, in some cities in China or in India, the data tend to be not as complete. And to help the local authorities really understand their own cities and better plan, for example, infrastructure or support offerings, we can develop what we call a global urban footprint from space. So this is really exciting because we can look at these radar data again that I showed earlier, and we can really, by using something that's called SAR tomography, which is kind of asking where do the buildings have to be to end up with the pictures that we're seeing, we can generate 3D point clouds. Here's an example from Berlin, where you can really see the buildings in 3D. And you can also even see the roads and the lampposts on the road, because just we have such a good resolution from the satellite images. And of course for Berlin we also have this data. We just did this to verify that a method is working, but we can do this for other cities as well around the globe. And then end up with a 3D reconstruction that may look like this. This is my hometown, Munich. You can see the university where I'm working in the top right there. And we can reconstruct all the buildings in this great detail from space without ever going to this place, which is quite amazing. And then in the end, the data product that people can use or local authorities can use is this global building footprint. Here we have an example from Cairo in Egypt, where you can see where the city is developing, where you have like very organized communities in the right here, where we have more unstructured communities like in the top or in the bottom. And oftentimes this is data that is not reflected in the records of the local government. So they may not be aware that there is some settlement developing in this area, but now from the satellite we can see it, we can tell them, or they can come to us and ask us. And then they can, for example, build a new bus line or a new subway or whatever. Okay, so I said we can also detect changes. This is a project done by my former colleague Lucas, which I think is really cool for rapid disaster response. So once again, this is the harbor explosion in Beirut in 2020. Some of you probably remember this. It was a big news headlines. There was a large explosion in the harbor of Beirut in Lebanon. And here we can see on the left an image before the explosion, on the right an image directly after the explosion. And you can see that there are some large buildings very close to the waterfront that were damaged by the explosion. This is really easy to see. But there are also smaller buildings that were damaged that are very hard to see, and we don't want to go in there manually tracking all the buildings that were damaged. So he developed a method which is called sibling regression, where you can then extract really which buildings were damaged or destroyed by this explosion. You can do this completely automatically. You just throw in two images, one before, one after. And it will tell you, hey, these are the areas to look at. Something changed in these areas. It doesn't tell you what changed. It just tells you, hey, we need to look here. And then we can give this data to the local authorities and let them know, hey, this is the specific areas you need to look at and need to send people. All right. Next up, this is a very dear topic to me, monitoring the climate and the environment. So we're talking about melting glaciers. We're talking about thawing permafrost. We're talking about pollution, like plastic in the ocean, this kind of stuff. And these are all things we can also see or monitor from space. So in the background here, we have a satellite image from 2016 in Antarctica, the Antarctic Peninsula. And what happened in 2017 is a super large iceberg broke off to the right. This thing was more than 5,000 kilometers squared in size, which is half the size of the Nevada region, so it's really big. And these events happen, of course, not just on this big scale, but also every day on a smaller scale, all across Antarctica, in Greenland, in all these regions, and nobody can look at all the images. So once again, we turn to AI to monitor this thing. And for example, one study we just recently published, or it's under review still, it's available, but it's not reviewed, so probably not fully published. But I'm really proud of this, where we analyzed the archipelago of Spitsbergen in the Arctic Sea. And we just analyzed all the glaciers that are in Svalbard that are marine terminating, so all the glaciers that flow into the ocean. And we did this for the period from 1985 to 2023, so a really long time series as well. And this allows us to see which glaciers are advancing, which are retreating, and how is changing temperatures, changing water temperatures affecting these glaciers. And what's really interesting is we can put this together with the ocean currents in the red and blue there. You can see warm water coming in red, blue water coming in blue. And we can see how this different ocean currents affect the glaciers in terms of their advance and retreat behavior. Okay, another thing, permafrost, which is my main research topic at the moment. We have large areas in the Arctic covered by permafrost. Around 17% of the global land surface is covered by permafrost or underlain by permafrost. And it has a global effect on climate, right? You may have heard of this carbon feedback cycle, where there's a lot of carbon and methane stored in permafrost. Permafrost thaws. This methane is released into the atmosphere and then further accelerates climate change. So we are really afraid of what might happen there, and therefore want to closely monitor permafrost. The main issue, however, is permafrost is underground. We can't see it directly from space, but what we can see is what's going on with permafrost. For example, here on the right, you can see a visualization of a so-called thaw slump, which is like a landslide that occurs when permafrost is thawing, and the previously frozen ground, which is very stable because there's lots of ice in it, it thaws, and the ground becomes unstable and then kind of drains away, leaving these big brown scars that we can once again see from space. And we did this in a study here, where we can see on the left, you can see these like pink areas. They appear pink in this visualization, but when you go there, they're more like brown. And they're very small. They're very spread out. The Arctic is huge. So we're mapping them with AI in order to just get a feeling for where are these things. Because when you send people to the Arctic, they can maybe visit an area like this, and then they have to go home again, because just it's too large to look at it all by going there. So mapping them from space is really the only option to get a pan-Arctic or global data product of these disturbances. And just for you to get a feeling of what we're mapping and how quickly these guys are growing, this is an example from Siberia in northern Russia. We can really see over the time span of 2 years that this whole peninsula is kind of just completely scarred by these permafrost thaw slumps. And we're mapping these not only because of this climate feedback, but of course you can imagine this is also very dangerous when you have a road, a railroad, a gas pipeline or anything sitting there. The ground goes away, of course you have large implications for the infrastructure. That's why we need to be very aware of where these things are happening, and maybe even predict this area is now rapidly growing in thaw slumps. Let's take care of the highway that's going past it. All right, and finally I was talking about pollution, identifying plastics from space. This is using yet another different type of satellite, which is called hyperspectral satellites, which is really cool because it gives us not just a few color channels, but really the spectral information of how the ground reflects the light. So we get around 100 or 200 spectral samples, and then can really compare the spectra of what's happening down there with existing measurements of different plastic types, or anything really, but in this case it's plastics. And we can see here that we can really, from this data, detect different types of plastics. For example, here this is construction sheeting in red. We have other things like sports fields in purple, or just solar panels and other kinds of roofs. And they all are made from different types of plastics, and by looking at these spectra, we can see which types of plastics are on the ground, see which are the ones that we care about that pollute the ground the most. And also, you can see here this close to the ocean. Of course, we have lots of plastics in the ocean, which is also really important to look at and understand what kinds of plastics are there, how we can take it out, how we can break it down, just by understanding the composition. All right. Earlier I was talking about agriculture and droughts, how we can see these in an early stage. And of course the methods are super complicated, so I just want to show you some pictures here about what this looks like in practice. So this is a region in Austria, northern Austria, where we had a large drought event from May to September 2018. And you can see just by looking at the images right in the top one, it's pretty green, everything's growing, and in the bottom it's kind of yellow, brown, lots of dried up plants. And now, by pushing this thing through our prediction algorithms, we can really get a very good impression of the plant health at each point in time. And we can see in the top one, there's very good plant health for most plants, and in the bottom, most of them are dead or shriveled away. And by comparing this throughout the year, we can, for each individual parcel of land, which is really cool because we don't just see the region, we see really every single farmer's field. Every farmer can go and look at their own field, how it's developing over time, and if there's need to be concerned about drought in this year, the harvest could be good or bad, how much will be harvested. Okay. Now, finally, for the last part of my talk, I'd like to talk about reasoning in Earth observation, which is what my research group is doing, and I think it's a really important topic. On the bottom here, you can see some faces that are working in this group or closely with this group. You might know this one guy there, Javier, who's also collaborating with us on reasoning topics. You know me, of course, and the other guys are mostly at TUM and the German Aerospace Center working on different topics related to reasoning. Okay, so people often ask me, Konrad, what is reasoning, right? You work on reasoning in AI, but what is it? And it's a very tough question to answer because we don't have a clear solution to reasoning. But it's much easier to show you what isn't reasoning. So in this case, I did this last week. I went to a very famous chatbot and asked it this very simple mathematical or logical riddle, which you could probably ask people in the first semester and they would be able to solve it in 5 minutes. So is it possible that Mrs. Miller here has children where each kid has one brother and one sister? And if you think about it, it's not possible. And it's very easy to prove that mathematically, but if we ask ChatGPT, it says yes, it's possible. And it gives us an answer. So Mrs. Miller has 3 children. 1 boy and 2 girls, and then each child has 1 brother and 1 sister. And if you look at this situation, it of course doesn't make sense because the 1 boy has 2 sisters but no brother. But the model is very confident that this is the right answer. And without thinking about it, really like being critical about this, we think, okay, it says yes, so it's probably possible. And while this is a very simple fabricated example where there is a clear answer, this becomes very dangerous when we look at more complicated examples and just trust the model prediction, because clearly there's some building block missing in this model to handle kind of logic and relationships between different objects. And of course, we're not the only ones who think that reasoning is important. If you look at AI news, you often see headlines like this. Millions and billions of dollars invested in reasoning for AI because people realize that this is something that's currently missing. And what I want you to take away from this slide is that it's very important that we work on reasoning, and also it's a very active research area, so nobody has a clear solution on how to do this yet. So the best thing we can do for now is just try different approaches and see if they work. Now, specifically in Earth observation, okay, one more example, sorry. One very good way to think about this is that we basically have 2 modes of thinking or perceiving the world. The left one is perception, so if I show you this image and ask what animal is it, you just immediately know it's a penguin. You don't look at the beak or the wings or anything and say, oh, this pointy beak, it must be a penguin. You just know because you perceive it naturally. And if I show you the Sudoku riddle on the right and ask what number goes in the yellow square, You probably don't know. Some genius might, I don't. So what you need to do for the Sudoku is you need to go step by step, like have intermediate results, go and have this chain of reasoning, which is really the fundamental issue between perception and reasoning. And perception here on the left is something that AI is currently very, very good at, probably better than humans. But reasoning, not so much. So if you give the Sudoku to ChatGPT, I don't know if it's going to figure out what's in the in the question mark. I guess not. But yeah, that's what we're working on, like getting this to work. So in reasoning, we are operating on these mathematical ideas like discrete symbols or tokens that have specific values, and we care about the relationships between objects or concepts. Reasoning tends to require multiple steps. It's very uncommon for a reasoning task to be answered in a single step, but it can help us to reveal things or insights that we didn't know in the beginning. So this is a very tough situation that we're in because we want to connect Earth observation with reasoning. And on the left here, Earth observation, we have this kind of continuous imagery data. We have real-world concepts which tend to be super fuzzy and not mathematically well-defined, right? Where does a tree begin? Where does it end? Does it include the leaves when they fall down? All these different kind of questions. And on the right, we have this very logical world of reasoning, which consists of discrete tokens and abstract concepts. So the question is, how can we kind of bridge the gap here? How can we apply ideas from reasoning to Earth observation? And for that, we're looking into 3 strategies. First, we can reason across modalities. So, for example, connecting text and imagery, connecting imagery from different modalities like the radar imagery and the optical imagery, and reason about the relationship between these modalities. We can reason across time, looking at multiple time steps, and see what happened there. How did these objects change over time? And we can reason across space, which is what I showed you earlier, like reasoning, okay, the car is on the road is next to the building, the park is next to the road, blah, blah, blah. So like looking at spatial relationships between objects. Okay, and I'm just going to show you some works that we do in these 3 areas. So I'm going to start with the modalities. This is not our work, this is from OpenAI, but it's a very successful concept that lots of our work builds on, which is called contrastive language image pre-training. And the idea here is that I have images, and for each image, I have a text caption or text description. And what these guys did here is they have one neural network model that kind of extracts the information from the image, and one model that extracts information from the text. And then all they do is say image and text representations from corresponding images and text should end up very close to each other. And if it's from different, like if the text doesn't match the image, it should be very far from each other. And that's what they call a pre-training task to extract information from both imagery and text. And it's a very simple way to connect this continuous world of imagery with the discrete world of language, where we have separate words which are kind of discrete tokens. And the cool thing is, just from this pre-training, the model gains some reasoning capabilities. If we look at a very popular benchmark here, it's called Clever, where we have 3D generated scenes looking like this here on the left, and then some questions about these scenes which require reasoning. For example, down here, is there an equal number of large things and metal spheres? We have to go in multiple steps. How many? What are large things? How many are there? What's a metal sphere? How many are there? And then compare these 2 counts. And the cool thing is that just by this contrastive language image pre-training, because we were connecting language and imagery, we can outperform many other baselines without changing the model at all, just by applying this pre-trained model to this data set. So combining language and vision is a very strong contender for reasoning that we're also exploring in Earth observation. Going more into practical stuff that we're doing, this is a project here by Zheng Heng, one of the students from the group, working on visual question answering. So it's very simple to what I just showed you. You have an image and you have a question. And the model then needs to answer correctly to this question. For example, we give you here this aerial image and ask, is there a road in this image? Then the model needs to understand the image, it needs to understand the question, and then finally combine these 2 informations to answer correctly in this case. And what Zheng Heng notices is that there are different kind of difficulties, right? So is there a building present is a very simple question, but what fraction of the area is covered by residential buildings is a very tough question. And when we teach, for example, a baby or a child about the world, we don't start with very difficult questions or very difficult concepts, right? You don't teach a 3-year-old multiplication. You start by teaching him, hey, this is a duck, this is a motorcycle, whatever, just very simple concepts, and then you can go to the next difficulty steps and have this kind of incremental learning where you start with simple and go to hard. And this also works really well with neural networks. So in visual question answering, when we start with the simple questions and then gradually go to the tougher questions during training, the model will end up much stronger in these reasoning tasks than when we just give it all the hard questions from the beginning. Another thing that she's currently working on, she's kind of our NLP guru, I would say, is referring image segmentation. So you have an image and you care about some type of area in there. So this can be the roads or this can be the buildings. Like I said earlier, different people care about different things in these images. And sometimes they care about stuff that wasn't in the training set. So for example, if I care about, in the bottom right here, low vegetation surrounded by buildings, some people might care about that. We can just, for this model, give it a text description of what we care about, and it will give us the precise location of these objects or these areas in the image, even if that wasn't in the training set, because it has learned how to connect concepts in the image, in this case vegetation and buildings, in order to answer us queries with contextual clues. All right, oops, am I on time? Let me check real quick. Okay, I need to come to a close, I guess, but we're almost done, don't worry. So another thing that we can do is we can not only connect natural Earth observation with text, but also with audio. This is a very fun project that I was working on last year, and the year before that is where we do essentially the same idea as this clip model. We have imagery and audio taken at specific locations, and then we ask our models to, again, extract information and connect image and audio if it's from the same location, and make the representations different when it's from different locations. And just by doing that, we get an improvement on downstream tasks like classifying images or segmenting images, because this requires the model to somehow connect these two modalities, which are super different, in new or innovative ways that it otherwise would never have done. All right. I said we can also reason through time. So if we look at this image, this is actually what most remote sensing images look like. You have clouds everywhere. But we care about what's under the clouds, right? We want to see through the clouds. We want to know what's happening on the ground. And one easy way to do this is we can look at maybe the next image or the image after that. And here we can see there's a sports stadium there under the cloud. That isn't super interesting, but if we look at more images from time, we can see a month ago there was a construction site. So this was just recently built. And this is what we can do with remote sensing time series. We can put them into a temporal context and understand where things are changing, where things are newly built, where things are torn down, and also what is obstructed by clouds. And of course, this is a very fabricated example, right? I selected this just to show you, okay, there's something going on. But in the real world, we have projects where this is super important that we exploit all the temporal information possible. For example, here my colleague Paul is working, this is his data set. Really, really messy data. And he's working on detecting landslides in areas like Indonesia or India and these kinds of areas where it tends to rain a lot. And the annoying thing is landslides are triggered by heavy rain. So whenever there's a landslide, there's probably also clouds around. And the question is, can we now, from this super messy data, extract when these events are happening and where these events are happening, even though we have clouds everywhere? And for that, of course, we need to use all these data that we can get. We cannot wait for a cloud-free image. We have to use these messy data to understand what's happening. It's a very tough task. But Paul is slowly making progress, and it's a really cool project, I think, because it's really supporting regions that are heavily affected by these landslides if we can precisely map this thing. And it's something that, from this cloudy imageries, nobody has been able to do yet. All right, finally, this is the last topic, spatial reasoning. If we look at the sandy area here, we don't know, is it a desert or, I don't know, a beach? But if we zoom out, whoops, we can see, okay, there's an ocean nearby. And that actually influences our perception of the beach. because by knowing that there's water nearby, we know this sand has to be a beach, right? So we look at spatial relationships between objects to understand what they are. And that's exactly what we want to do in spatial reasoning. We want to use contextual clues from surrounding locations to understand what's happening. And this is especially important in remote sensing, where we just have so many different objects on the ground that are related to each other. And what are we doing there? For example, spatial representation learning. This is once again my permafrost study, where we can see here we have some area in the permafrost region. And what we did in this example is we just asked the model to come up with any segmentation of the imagery. Assign one class to each pixel. We don't care how you do it. You just have to follow these two rules. You must use all classes that we give you. And when we rotate the image or mirror it or something, then the segmentation must remain the same, right? So just the patterns that you detect must be stable under when we change the image, when we look at it differently. And just from these very two simple rules, the model learns to give us something like this. Map spatial patterns, detect lakes, detect mountains. And what's really cool, it also learns to kind of detect our landslides, our permafrost landslide that we're looking at, which is here, this yellow class. Right, so it's highlighted now. These are the things that we're looking at, and without ever teaching the model what we're looking for, it was able just from these simple rules to come up with kind of a segmentation that gives us what we want, that we can then work with. All right, and I promised you one study about this GNSS reflectometry. So in this case, spatial reasoning, space doesn't always look the same. In this case, it's some kind of elliptical signal that we're looking at. We don't really know how to make sense of that. And conventional vision models don't know how to work with this kind of data because they're used to working with natural images. So what I've seen here, my colleague came up with, is we can use different models, in this case vision transformers, which can learn to perceive the world in a different way by dynamically adapting how they see the signal. And then by doing that, you can now use this imagery to extract the wind speeds across the oceans. And from this change in model, from a vision model to this, it's still a vision model, but it's a different vision model that can adapt the way it looks at the world, we can get much better results just because we change the spatial perception of the scene. All right, so let me conclude. Artificial intelligence and Earth observation, it helps us understand large satellite data. It's super important for researching things like urbanization, climate, agriculture, and perhaps as a motivation for some of you who want to start working in this field. It's very active and very exciting, super important research, and I'm happy to be part of it. Thank you for your attention.
Thank you, Konrad. So now it's time for the questions. You want to ask any question to Konrad? Okay, I will ask you some questions. So you have spoken about different types of satellites. If you would need to decide just one type of satellite, what would be?
I get just one?
Yes.
Very tough question. So I'm a big fan of the ESA satellites, probably the Sentinel-2 satellite, because it's quite high resolution, right? You can see a lot of things there, but we can also get data quite often. So around every 5 days we get a new image. So it's kind of a good compromise between high resolution and also good availability of the data. It's all free.
Do you think that it is possible to apply uncertainty principles to reasoning? For example, it's important to know if the reasoning is okay or not.
Right, if you look at these topics like reasoning, uncertainty, explainability as well, they're all kind of connected, right? And ideally in the end we want to have it all. And there are approaches to what's called probabilistic reasoning. So not looking at this is true and this is false, but this is probably true, this is probably false. It can be done. The formulations are usually NP hard. It's very tough to integrate that into a deep learning model. But I've seen people try to do it, and of course, if it can be done successfully, that would be super exciting, yes.
I wanted to ask if you could elaborate a bit more on the drought prediction that you mentioned, because I mean, the second picture that you've shown here in the field, you can also
Exactly. So maybe I can elaborate a bit more on the project. What we're doing there is we work together with an agricultural insurance. So they insure the farmer's field in the case there is a drought. And what happens is now at the end of the year, the farmer comes and says, hey, I had a drought on my field. And then the insurance has to send somebody to that field and really like count the grains and look at the things, which you can imagine is super laborious and expensive for the company. So they were looking for ways to like green light easy cases, right? So if our AI model says, okay, with 99% probability there is a drought here, we don't have to send anybody. That was kind of the motivation for that study. But of course, as you said, most information is in this kind of this curve over time, the greenness or also the infrared spectrum, and that's also what we ended up working with. Did that answer your question? Yeah. Okay, cool.
I was wondering about climate change monitorization and all of these permafrost project, for example. Like, how is it the institutional collaboration? Like, for example, right now, is it just ending in a paper and then very interesting presentation, or is it like there is something that we form and
Very good question, because that tends to happen, right? You have a research paper and then nobody looks at it ever again. But in this case, it's a very active collaboration with Alfred Wegener Institute in Germany, which are one of the big research institutes regarding permafrost. And so they are really out there in the field collecting data. We are looking at it from space and really working together to better understand the processes there. And then, of course, we're not there yet fully to understand what's going on. But we hope to one day like combine all these insights into understanding where is permafrost thawing, why is it thawing, how quickly is it thawing, when's the methane released. So it's part of a bigger picture.
Okay, I have just another question. Today, we are speaking about generative AI. Do you see any application of generative AI in your work?
I think generative AI is super exciting, and I've tried some project with it, but never was able to get it to work quite as well. But I see many potential applications, for example, for estimating uncertainties, because generative models work with probability distributions. I think there's a poster over there exploring something similar. So there's definitely potential in combining generative methods with, in this case, Earth observation.
Okay, so thank you, Konrad.
Thank you.